Hello, everyone. This is chapter 16, Chemical Kinetics. Today we will be discussing the main topics of chemical kinetics, definition of chemical kinetics, the general expression for the rate law, and also some examples related to calculation of the rate based on concentration data. Okay, so let's start. Definition of chemical kinetic is quite straightforward. Kinetics is the study of how fast a chemical reaction takes place. And by chemical reaction, we are talking about the change in reactant to the product side. So the chemical kinetics in this chapter focuses on reaction rate, the change in the concentration of reactants or products as a function of time. So when you look at how the concentration of reactants or products changes over time, we're really focusing on chemical kinetics. If we have a general reaction, which is shown here, where the coefficients lowercase a, b, c, d are the stoichiometric coefficients or the coefficients of the balanced equation, we can express the rate of that reaction according to the definition of the chemical kinetics to be rate equal to the negative inverse of the coefficients for the reactants times, so basically this is the negative inverse of the coefficient for the reactant A, times the change in concentration of reactant A over the change in time. So this square bracket, which is explained later as a, in terms of its notation, the square bracket enclosing A basically refers to the concentration of A in moles per liter or molarity of A. So we're talking about molarity of A when we place any of these components inside the square bracket. So this basically means the change in molarity of A over the change in time. Delta means change, right? Okay. And also, it can be expressed as the negative inverse of the other component, reactant B, the same way. But for the product side, we don't include the negative sign. However, we have everything else. We have the inverse of the coefficients, we have the change in concentrations over the change in time, but that negative sign is not there. The reason we don't include the negative signs in the expression of the rate for the product is because as time goes by, as time increases, the concentration of the products increase as well. So there's a direct relationship between the change in time and the change in concentration. However, for the reactant side, as time goes by, as delta T increases, delta A falls, the change in concentration decreases. So there's an inverse relation between the time and the concentration of the reactant. And that inverse relationship is expressed as a negative sign in front of that coefficient. Okay, so it's a good idea to know this expression for the rate of any general reaction given here. Okay, so let's go to the next page. The next page basically it walks you through the notation that we have used for equation 1. It's basically telling you that the square bracket indicates a concentration in moles per liter or molarity, and the unit of rate is also important to pay attention to the unit of rate. The unit of rate is molarity over second, because it's the change in concentration, which is molarity, over the change in time, which is second. Okay, so S is second, M is molarity, or if you want to break it down in terms of moles per liter, it would be moles divided by liter times second. Okay, And I've also indicated that the negative sign is indicated for the reactant in that expression and not for the product, which we already mentioned. Okay, now the rate law and the component of the rate law is a very important section that we need to focus on today. So basically, if you are studying a general reaction of the same type that we discussed before, AA plus BB going to CC plus DD, the rate law is written as rate equals to K times the concentration of the reactant A to the M times the concentration of the reactant B to the N. Now, what's important about this rate, and this whole expression is called the rate law for that particular reaction. What's important here is that there is no product appearing in the rate law. Okay, we don't have C or D in the rate law. We only have A and B in the rate law, which they are referring to these reactants A and B. And also, the exponents M and N are not necessarily A and B appearing here. Okay, so we'll come back to that. But let's just go over the notation here since we have the rate law. So the K refers to the rate constant, which is always temperature dependent. M and N are called reaction orders. As a matter of fact, M is called the reaction order with respect to A, and N is called the reaction order with respect to B. And of course, we already mentioned this, that A enclosed in the square bracket stands for the concentration of A in units of molarity. So two key points to remember about this rate law expression, which is equation 2. Okay, so the balance coefficients A and B in the general reaction are not necessarily related to the reaction orders M and N. In other words, we cannot just basically write a rate law based on the balanced coefficients appearing in that equation. Okay, we don't know what they are, and that's why we leave them as M and N, because they have to be determined by the method of initial rates that we will discuss in the next section. Okay, so A and B are not necessarily appearing in that rate law equation, okay? M and N are not the same as A and B. The components, the other key point is that the components of the rate law, which are the rate expression itself, the reaction order M, N, and the rate constant K, we collectively refer to these as the components of the rate law. So basically M, N, and K are what we are calling the components of the rate law, okay? They must be found by experiment. And in the next section, we are going to actually take a look at that particular experiment, which is called the method of initial rates to determine M and K, therefore all the components of the rate law, and therefore the rate expression itself. Okay, a matter of notation here, we are going to be referring to first order reactions, second order reactions. So let's just quickly go over these before we get underway with the method of initial rates. The first order reaction. So basically, if you have a reaction of the type AA going to BB, and we know it's a first order reaction, then we can write a rate law basically writing rate equal to K times the concentration of A raised to the first power. That's important. That first power indicates this is a first order reaction. So the reason we call it the first order reaction is because the power of A is equal to 1. Now, so and I've explained here at the bottom of the page that since A is raised to the first power, the order of the reaction with respect to A is 1. Therefore, first order with respect to A. So remember, M is called the order of the reaction with respect to A. So if M is equal to 1, then we call that a first order reaction. Okay. Now, what about a second order reaction? A second order reaction is defined in the same way, except that A is now raised to the power of 2. So the exponent of A, which is the order of reaction with respect to A, is 2. So for any second order reaction, we can simply write rate equals to K times the concentration of the reactant to the power of 2 squared. And again, note that no product appears in the rate law expression. Okay. So now we say that reaction is second order with respect to A, or simply just second order. Okay. So the exponent of A basically determines the order of the reaction. Okay. Now, for the reaction that we have here, this is a combination reaction between NO2 and carbon monoxide to produce NO and CO2. That's a sample problem on page 705. It's sample problem 16.3. And we are here trying to find the exponent Mn for this reaction and also K. So there are 3 components we need to find. We need to find the order of the reaction with respect to nitrogen dioxide, NO2, and also the order of reaction with respect to carbon monoxide, CO. Now what we have been given is basically a table of data that is referred to as the method of initial rates. So this is basically an experimental method that I referred to in the previous section to determine Mn and K. After we determine Mn, we can determine K. So first we start with M, N, and then K in that order. Okay? So we have been given 3 experiments. The initial rates for each experiment is given. But as you can see, the initial concentrations of the reactants also given. Now, what's important to realize when you look at this table is that going, for example, from experiment 1 to experiment 2, one of the components' concentration is held constant and the other one is changing. So the concentration of CO, for example, going from 1 to 2 is held constant, is fixed, and NO2 is changing. If you look at 1 and 3, for example, 1 and 3, you can see NO2 is held constant and CO is changing. Okay, so the reason we have that is actually that is intentional. We are trying to basically going from one experiment to the other, fix the concentration of one component or one reactant and change the concentration of the other one. So it would be easy for us to work with the different variables that we have in calculating M and N. Okay, so the question now is, okay, so let's say this data is given to us, and which is called the method of initial rate data, and now we are trying to find M, N, and K. How do we do that? So to solve for each component, M or N, we take the ratio of the rate law for 2 experiments in which only the reactant in question changes and the other reactant stays constant. For example, to calculate M, we take the ratio of the rate law for experiment 1 and 2, in which NO2 changes but CO is kept constant. Okay, so if you take the ratio of rate 2 to rate 1, and then you know that the rate law for experiment 2 can be written as mentioned previously as KNO2 to the M, CO to the N. The subscript here indicates that these concentrations refer to experiment 2. Or the subscript 1 here refers to the concentration of these components appearing in the table and labeled as experiment 1. So therefore we have 2 and 1 to distinguish the experiment 2 from experiment 1. Okay, now Now, if you look at this expression here, you see that the concentration of CO in experiment 2 and experiment 1 is the same. So we can cancel them right away. And we also know that K is a constant. It doesn't change from experiment to experiment, so we can cancel them out as well. Okay? So now we are left with the concentration of NO2 in experiment 2, concentration of NO2 in experiment 1 raised to power of m. So as you can see that we can substitute basically for those rates. Rate 2 to rate 1 is 0.08 to 0.005. And this is basically initial rate to initial rate 1. Okay? And the magnitude of those are given in the table. So we just substitute that here. And also, we note that the concentration of NO2 in experiment 2 is 0.4, and the concentration of NO2 in experiment 1 is 0.1. Okay? So this ratio refers to the initial rate 2 to 1, and this refers to the concentration of NO2 in those two experiments, 1 and 2. So 0.08 divided by 0.005 is 16, 0.4 divided by 0.1 is 4, and therefore that number is raised to the power of m. So 4 squared gives you 16, so m must be 2. And I've also indicated here at the bottom of the page the same thing that I just explained, that K's are constant, they cancel out, and CO2, CO, the carbon monoxide, in both experiments are held constant, so therefore we can easily cancel everything out except the concentration of NO2 that you're dealing with. Okay? And I've also indicated that it's best to refer to the table to verify those statements. Okay, now, to calculate N, which is the order of the reaction with respect to the other component, CO, we take the ratio of the rate law for experiment 1 and 3. Why 1 and 3? Because now, going from 1 and 3, you're comparing 1 with 3, you see that the NO2 concentrations are constant, and the CO is changing. Okay? So we set it up pretty much the same way as the other part, but now you can see that, well, I mean, we just do the cancellation the same way. K cancels K, NO2's cancel, and now we see that the concentration of CO is 0.2, the concentration of CO for experiment 1 is 0.1. We substitute the numbers in, and we get basically this 0.05 is the rate 3. 0.05 again is rate 1. Okay? 0.2 is the concentration of CO for experiment 3. 0.1 concentration of CO in experiment 1. Everything is raised to the n, so it's 0.2 divided by 0.1 to the n. Now, 0.2 divided by 0.1 gives you 2. This ratio is equal to 1. So now the question is, 2 to the n is equal to 1. What is n? So you know that any number raised to the 0 is 1 except 0 itself. So n has to be 0. So basically what we have is m equal to 2 and n equal to 0. So the rate law now becomes K times NO2 squared, because m is 2, and CO to the power of 0 because n is 0. And again, anything to the 0 is 1, so it becomes just simply K NO2 squared, which basically means that this reaction is second order with respect to NO2, and it's basically second order overall, and CO does not affect the rate of the reaction. So the reaction is second order with respect to NO2. So this is an example that has been outlined in the textbook in that problem. But the last component that we need to determine is K, the rate constant. So finding K is actually the easiest part of this problem, because we can go to any experiment to find K. You can go either to experiment 1, 2, or 3. I chose experiment 1 because that's what the book did as well, and I just wanted to be consistent with the book. So for experiment 1, we know that we are going to use basically this expression here, because now our new rate is this. It has no dependence on CO. We found out in the previous case. So the rate is going to be K times NO2 squared. You know that. So all that we have to do is to find the concentration of NO2 from experiment 1, plug it in, find what the initial rate is from experiment 1, plug it in, and we easily find K. So that's what I've done. The rate for experiment 1, 0.005, the concentration of NO2 in experiment 1, 0.1, and it has to be squared, of course, times K. So K is this number divided by the square of that, gives you 0.5. In the next video, we are going to basically talk about why the unit of K is per molarity per second. And we will find out actually that we will learn that if you're dealing with a second order reaction, that is the unit of K, where the unit of K for a first order reaction, for example, will be different. So again, to find K, we don't necessarily have to go to experiment 1. We can go to either 1 or 2 or even 3 to find the K. All we have to do is to find the appropriate rate and the concentration of NO2 for that particular experiment, substituted in the equation of the rate or the rate law to find K. All right, I hope this was helpful to set up the basic topic or the main definitions of the chemical kinetics, because in the next video we are going to take a look at the main components of chemical kinetics, which are the first law, second law, or first order reaction, second order reaction, and Arrhenius equations. And also we are going to take a look at mechanisms of chemical reactions, and we will be using some of these basic concepts that we just described today to work those problems. Okay, have a great day. Until next time, have a good day. Bye.